So part of being able to be successful at systems by graphing is to be able to identify the number of solutions. And also what that solution is. Right now, we'll just focus on what number of solutions it has. So look back at your definition for a solution. So for graphing, it's going to be the ordered pair that the two lines intersect. So how many solutions does graph A have? Well, one solution. The red line and the blue line meet here. That ordered pair would be my solution, and there's only one area that they intersect. Agreed? Anyone think they intersect at more than one spot? All right, so that's one solution. Now graph B, there are two lines here. You can't see the other line, why? Because they're on top of each other. All right, so they happen to end up graphing in the exact same spot on the same line. So how many solutions would that have? Infinitely many solutions. Good. All right, because if the solution is where the lines intersect and they happen to be right on top of each other, then anywhere on this line are solutions for, both systems. I mean, there's infinitely many because they go on infinitely. Over here, how many solutions do they have? No solution. Why? They're never going to meet. Why? Because they're parallel lines. Parallel lines never intersect. Parallel lines have what the same? The slope is the same for parallel lines. All right, so parallel lines never intersect. All right, just like how it looks here. So that's why there's no solution. The solution is where they intersect. Questions about that? All right, so then scrolling down. So these definitions up here, super important. Down here, a little less important. I'm not gonna lie to you. I have seen it pop up on tests in the past, these definitions down here. But so far I haven't seen it on your upcoming tests. All right, if it is, I'll let you know. Sometimes we include a vocab section, but for right now, just kind of try and understand it. So first we have a consistent system. All right, a consistent system is a system with at least one solution. All right, consistent systems can be either independent or dependent. All right, so scrolling back up here for graph A, B, and C, which of these are consistent? So look at your definition, they have at least one solution. So which ones would it be? Good, so graph A is consistent. It has at least one solution. Is graph B consistent? Infinitely many, is that at least one? So again, consistent. What about graph C? Good, it has no solution, so it's not consistent. What would be the opposite of consistent? So this one is inconsistent. And the way that I would remember it is like, is it consistent with the definition of a system? All right, so a system has the same variables. So there is at least one solution to those variables that meets both. All right, and stuff like graph C, there's no solution. So it's inconsistent with that definition, unlike the other two. All right, so we're gonna scroll down. I'm gonna kind of skip around here on the vocab. I'll fill in the inconsistent part. So that's the bottom blank. All right, an inconsistent system, and I'll just abbreviate it, is a system that has, what do you think? No solution. All right, so now back to where we were on this blank. So an independent system is what goes here. So an independent system has exactly one solution. All right, the graph of an independent system consists of two lines that intersect at exactly one point. So that's an independent system. I remember that one is like the independent, the I kind of looks like a one if you like write it, like a capital letter. All right, so scrolling back up, graph A, B, or C would be independent. Which one? Any others? All right, good. So only graph A is independent. So any graph that has one solution only is independent. Down here, this last definition. What is the opposite of independent? Dependent. So a dependent system. All right, so we talked about one solution, we talked about no solution. So what do you think goes here? Good, so infinitely many solutions. So a dependent system has infinitely many solutions. The graph of a dependent system consists of two coincident lines, which is really just a fancy word for saying what? Coincident lines are basically the same line. All right, so that would be our dependent systems. So would that be graph A, B, or C? B. And I'll like squeeze it in here. All right, so graph B is dependent and also consistent. Graph A is consistent and independent. Graph C is just inconsistent. All right, I'll let you know if we're really stressing the vocab on this next test, but just in case, here it is. Questions? All right, so then backside. Now it's the actual solving. All right, so this is the important one. There's actually 3 methods to solving systems. Today we're just learning one method, which is to graph them. All right, now to be able to graph a line, what form do the lines need to be in? Good, you're both correct. So slope-intercept form, y equals mx plus b. For example A, are they in slope-intercept form? Are either of them in slope-intercept? No. So I have to actually rearrange both. So I'll just start with one of them, 2x plus y equals 6. When we're trying to get something in slope-intercept form, what needs to be isolated? So how can I get rid of the 2x that's next to the y? Good. Now, if you remember, we spent a good chunk of time doing this last week. Prepare us for this right now. All right, so we subtract 2x from each side, and my equation in slope-intercept form is Good. I'm going to, I guess you could say like box it up. It's not my answer. But I'm gonna box it up or highlight it so I know that this I need to graph. All right, and I'll actually graph it now. Usually I'll rearrange them both and then graph it. I'll just graph this one now. When we're graphing, what do we always plot first? And my y-intercept is, and my slope is, since it's negative, do I go up or down? And then do I go to the right or left? Always to the right. Unless you're working backwards, which we'll definitely see some examples where we need to, like if you run out of graph. All right, but my slope tells me to go down 2 to the right 1. Down 2 to the right. I know in the past I've told you, just do maybe like 2 to 3 dots to make your straight line. For these types of problems, you're going to want to make sure that line is as straight as possible. So you probably want to do more dots. And you need to clearly see where they intersect. You don't want to have to like guesstimate it. Questions so far? All right, so now we need to graph the other one. Is the other one in slope-intercept form? How can I make it slope-intercept form? Good, this time we add x. So think just, what do I need to do to make this cancel out? So now my equation in slope-intercept form is good, thank you. Box it up, know that you need to graph it, it's not your answer. All right, and what's my y-intercept of the one in green? 3. So put a dot on the 3 on the y-axis, and my slope is what? So I'm going, good, it's positive, so we go up, and it's always to the right unless we have to work backwards, which we do not in this one. All right, because I can clearly see where they intersect. Where do they intersect at? 1, 4. All right, so 1, 4 written in coordinate form is my solution. All right, so this over here is my final answer. Questions there? All right, and it really doesn't get much harder than that. I mean, we'll look at what it looks like with the infinite solutions and no solutions, but as long as you can rearrange into slope-intercept form and graph 2 lines, then you're good. All right, so let's do another one together. Example B, are either of those in slope-intercept form? Which one? Good, so I'm just gonna kind of either box it up or highlight it so I remember to graph it. Is the other one in slope-intercept form? How can I make it that way? Isolate y. Now look at how it's written. It kind of looks like it's in standard form, but it's not exactly. Just remember, you have to isolate y. So how do I get rid of the 6x? Good, do that on each side. On the left side, what remains? And then on the right side, I have. Good, and I'm glad you guys got in the habit of putting the x term first so that it looks more like slope-intercept form. If you put 18 minus 6x, I mean, you're not wrong. Just make sure you don't get confused later on when you have to plot it. Opposite of multiplying by 3 is dividing. Do that on each side. Make sure you do it to each term on the other side. And my equation in slope-intercept form is good. So -6 divided by 3, 18 divided by 3. Here's my other equation in slope-intercept form that I need to graph. All right, so I'm going to graph the green one first, the one that's at the top already in slope-intercept form. So I need a dot on what number? So we're starting with the grade one. -2, and that slope was a +2. So we need to go up 2 to the right one, up 2 to the right one. And again, I would just put as many dots as needed, because we want to have a perfectly straight line. And then in the blue, y-intercept is, and my slope is going down. Good, down 2 to the right one this time, because it is negative. Do you already see like where it intersected? No. Yes. So then I'm still going to draw my line, at least the best I can. And what is my solution? Where did they actually cross? 2. Good, right here. I'll make it nice and big so you can not see that my lines are crooked. But +2, 2 is my final answer. All right, so if I plugged in 2 for the x and 2 for the y, you would see that they equal each other, right? And you can even do that in your head. What's -2 times 2? -4, and then +6 is 2. All right, I just did it in my head. I could work it out by hand, but I think you guys are fine. Or like over here, 2 times 2 is 4, minus 2 is 2, which is what our y equals. So it does work out. Questions? All right, try out the next two. I did hear a couple people mumble it. Yes, it is -2, 2. So remember, your final answer is the one that's in coordinate form. So this right here. All right, and the solution is where they intersect. Your guys' graph looks a little different than mine. All right, I changed them because my graph counts by 2s. All right, and I didn't like that. So your graph is just like a normal traditional graph. You guys probably realized you had to work backwards, which you'll see when we do a few more examples, what that looks like. But either way, just graph the lines. See where they intersect. If it doesn't look like they're intersecting to the right, then work backwards. When you have to work backwards, what do? You do the opposite of what it tells you to do. So instead of going down 1 to the right 2, go up 1 to the left 2, and keep working that way until you get a point where they cross. All right. If you have access to Desmos, you can graph both lines and see where they intersect. Now, keep in mind you're still held to the standard of showing work on your practices and stuff. But if you want to check that you did it right by plugging them in, go ahead. All right, that's what I would do on a test. Still workshop. All right, and then this stuff over here is just me showing you that if you plug in the x and y, they do equal each other. All right, that's what I was kind of talking you through in the last examples, but here it is visually. All right, when you plug them in, they do satisfy both equations. Questions about that? All right, and then the other one, the answer was -2, 4. All right, so that's where they intersect at. Any questions? All right, so we're moving on. All right, so now we're going to look at examples where the solutions aren't the traditional one solution. So example 2A. Still go through the same process. You really don't know until you at least rearrange them into slope intercept form. So in example A, are these both in slope intercept form? Is one of them? Which one? Good, so I'm going to highlight that one, make sure I graph that one. The bottom one though, it's not in slope intercept form. How can I make it that way? Good. On the left side, what remains? On the right side. Good, and then is it in slope intercept form now? Good, so we're gonna kind of highlight that one, make sure that we graph that one as well. All right, so starting with the one in blue, what's my y-intercept? Good, so find it on your y-axis. Not all the time is it labeled. All right, but just know it's below the origin because it's negative. And then my slope is 2, so I'm going up 2 to the right 1, up 2 to the right 1. All right, and then draw your straight line. Pretend that that's straight. The green one, what's my y-intercept? 4, my slope is, now can I, on this graph at least, go up 2 to the right 1? No, so this isn't a situation where you have to work backwards. So instead of going up 2 to the right 1, we need to work backwards, do the opposite. Go down 2 to the left 1. Down 2 to the left 1. All right, and then keep going. Does it look like they will cross at any point? No, because they are parallel to each other. Let me make this look more parallel. I kind of drew that off. All right, but yes, they're parallel to each other because they have what the same? The slope. So you probably noticed that in the equation. If not, then graph it and then you know for sure. If they have the same slope and different y-intercepts, then how many solutions does it have? No solution. Or 0. Yes, so 0 solutions, no solutions. All right, because again, these are parallel lines. They have the same slope, but different ones. Questions? All right, so now let's look at example B. Are either of them in slope intercept form? Yes, so I'm going to highlight the one that is, and then I'll make sure to graph that one. The other one we need to rearrange. How can I get the y by itself? Good. So add 3x on each side. Y is now by itself, and my equation in slope intercept form is 3x minus 3. Gonna go ahead and highlight that one to make sure I graph that one. But what are we realizing before we even graph it? They're exactly the same. They have the same slope, which I'll just put M. They have the same y-intercept, which I'll just put as B. So they are the same line. How many solutions do you have when they're the same line? Infinitely many. I know it's like a long expression, right? But it's infinitely many solutions. Because when I graph them, they intersect at infinitely many spots because they are the same line. So I'll just show you what that looks like. Okay, so y-intercept. All right, so y-intercept is -3. Slope is +3, so going up 3 to the right 1, up 3 to the right 1. And then when we graph the other one, oh look, it's exactly the same. Touching all the same dots. All right, it's the same exact line. All right, questions? All right, so try the next two, your turns. And I know I probably didn't need to graph it, but if on the test it says to graph it, then you better graph it or else you lose points. So for number 3, how many solutions did you have? Good. All right, infinitely many solutions on number 3, because when you rearranged it, it's the exact same line. Now the rearranging in this one was a little different than the ones we did like earlier today or like the ones we did last week, but you just need to know like, what do I need to do to make it 0? All right, so subtract x would make that cancel out. Subtracting 2 would make that cancel out. Okay, and then there you go. Number 4, you had how many solutions? 0 solutions, no solutions. Because when you graph them, they are parallel lines. All right, same slope, different y-intercepts. And you can probably just see it from the equation, which is great. That can save you some time on the test. But if it does say to graph it, then make sure you go through the steps of graphing it. Questions there? All right, and I thought about doing the word problems with you guys, but we do have a day next week dedicated to like just doing word problems. So I think I'll just skip that and we'll probably revisit it next week. All right, just what you end up seeing is that some of these methods, so today we only learned graphing, this week we'll learn like substitution and elimination. Depending on what the question is, sometimes it's better to use the other 2 methods, sometimes it's better just to graph them. All right, so your practice, if you need like additional graph paper, go ahead. Just know that like if you can do the stuff like we did in the notes, then you should be good for the test. Any questions?